Hello all. We are learning about various Simulink library basic blocks. Till now, we have covered various basic library blocks and various basic projects or logics implementation using Simulink library. Okay, now we will learn about how to implement Newton's law of cooling in Simulink. So, till now we have studied about the various basic equation, mathematical equation, or like some counter operations and some another operations. But here we are going to learn about the how we can integrate, how we can like design a integration equations or differential equations using this Newton's law of cooling. So aim to study is that the relationship, what is the aim behind the Newton's law is the relationship between the temperature of body and time. So that means the Newton's law of cooling says to us when our body is cool, then rate of cooling that is directly proportional to the body temperature minus like surrounding temperature. So you can see here now in this equation the rate of cooling here that d by dt. Okay, here that let's see that T of Tb the temperature inside a system and Ta is the temperature outside the system according to Newton's law of cooling. That is what I just now told you. The if our body is cool, then rate of cooling, that is this is the rate of cooling dt by dt, that is directly proportional to the body temperature minus surrounding temperature. So this is my body temperature inside the system, and this is the temperature outside the system. So this is my body temperature and this is my surrounding temperature. So that Newton's law of cooling says us our body temperature, like rate of proportional of like cooling is directly proportional to the differences between a body temperature and surrounding temperature. So here in this equation, dt by dt is equal to k into T minus Ta. So k is that proportionality constant, k must. So this is a derived equation. If you want to see more derivations, so you can go through this, how it will work and all this thing. This is our simple solving the equation with the first order or second order of the differentiation. Okay, now we can implement this equation dt by dt is equal to k into T minus Ta. That is our body is cooling, then rate of cooling is proportional to the body temperature minus surrounding temperature. So here I have implemented the basic logic with the help of this itself. Here I will be having input k. So you all know this equation. I'll make this equation here a little bit small in front of, so you will be easily able to understand. Okay, so now you can see this equation here. Okay, dt by dt is equal to k into T minus Ta. My Ta is a surrounding temperature, T is a body temperature, and K is a proportionality constant. So here you can see the K, the proportionality constant, I am taking as a 0.1, and Ta, like surrounding temperature, is a 20, and this is my like XO, what is my body temperature I am giving from here. Okay, and this is my like integrator, like I'm getting a differentiation with this integrator. So you can see this is my T minus T, this is my output of the integrator is becoming a T. So this is my the constant which I have to provide with respect to the time. Okay, T dash to how to with I have to integrate here. Okay, so this is a K into T minus Ta. Okay, so where from I am getting a T minus Ta. So here I am getting this integrator output as an T, and this is my Ta. So I have using here the subtractor here, plus and minus, where I will be T minus Ta, that operation is performing. So you can see on this line I have given a T minus Ta. We already discussed that naming convention to the each signal is very important. So here also I will give the name as a Ta, so that will be more easier, and this name T is coming itself from here, so it's not required to write it here as well. Okay, so this is a K, and output of this is equal to K in bracket T minus Ta. Okay, this is the output of this, and this is the t dash, means it is a t integrator where I will be multiplied with something, and after the differentiation I am getting a t. So in that way I have implemented this differential equation. I'll simulate. Now we can see the graph outputs for this. So you can see from the 60 it is coming down and it is getting a proportional at the end. Okay, temperature versus time. This is a graph of temperature versus time. So here, if you are looking about a few of the blocks, like this is integrator. Okay, if I'm taking a integrator from a continuous library block. So this is you, if you have to see the difference between here x0 I am getting. This is the initial condition which I have taken here to the initial condition from external. I am make this output, then this port x0 is created. So here also you can see this integrator. If I am making it double click, so here initially the properties are external. If I am internal, if I am making the external, then you can see that X0 port is created. So in that way, you can configure the integrator properties as well according to our specifications. And the rest of the basic block, these two are the constant blocks. This is a product block and this is a gain block. And this is a constant block and this is a scope. So that all blocks, rest of the blocks, you know. But the important difference was, like integrator, we have an option to take the initial condition internal, where I can write it here directly, or if I want like external, so that also possible. Both the things can I do where I want to do. If I am making it internal and writing a 60, that is also work. Okay, if I am making a external and connecting a constant here or something else, like some or mathematical equation, output should be the initial condition. Every time initial condition may be changed, may not be changed. There are various ways of operation we can perform with this integrator. So integrator is a continuous time integration of an input signal. Okay, so this is about the Newton's law of cooling, where we have learned about that the rate of cooling is directly proportional to normal body temperature minus the surrounding body temperature. So that's all about this. This is one of the basic example with a continuous library block, okay, which I have implemented. Thank you.